Hello and welcome to day 24 of 5 to 5. So first thing we're going to do here, we have multiple graphs and we are going to apply our standard technique of Oyzerga. Oyxirga. And the origin in this case, we have something that's is a little unique here. Our origin is like this. This is where the zero lies. So we have a quadrant 1 and a quadrant 4 down here. The y-axis is velocity in meters per second. The x-axis is time in seconds. And we can see here that we've got, it goes 0.51, 1.5, and so each one of those increments is a 0.1. The time, we have 5, 10, 15, 20, 25, like so, and each increment is a 1. We look at the intercepts. Our intercepts are here and here. And it looks like it comes back to an intercept right there with that curve. And let me just connect those to draw them out. That's the curve relative to the axis. All right, so those are our intercepts. And what can we read? All right, so this is becoming old hat. What we can read is the axes themselves, the velocity and the time, the instantaneous of each, initial, final. The gradient of the slope is delta V over delta T, which is the acceleration, which we could use dimensional analysis to figure out, or we could just know it from our formulas. The area is V times T, meters per second times seconds, which is M, and that gives us the quantity delta X. Now, we have used VT graphs enough at this point in the course that you may just remember what the slope and the area are. Keep in mind there are going to be 50 more different graphs before the end of the course, so memorizing what the slope or the area means on any particular graph is a huge mistake. Remember the tools and you can just always figure it out. If you rely on memory, you are going to forget, and especially since you may see graphs that have axes you've never seen before, you need to have a process for breaking them down. So don't bother memorizing them, please. All right, so the velocity over time, what is happening? It starts at 1, it decreases to 0, and then the speed increases again, but in the negative direction, and then it seems to immediately stop and head back in the other direction. So if we are to create a motion diagram of sorts, we'll create a one-dimensional number line with our positive direction, our negative direction like this. We don't really know where the thing is starting, but we do know that it starts quickly, and it's headed since it has a negative slope, positive velocities, we know that it's headed in this direction, in the positive direction, and that it's slowing down. And at some point, it comes to a stop, and we know that time is at about 7.5 seconds. And then it speeds up exactly the same in the other direction. So now, if we change the color of this, just indicating the different time, it's there, and now it starts heading backward. Let me make that a different color still, make it peach. It's heading back like this, getting faster and faster and faster. No, we noticed that it was traveling 1 meter per second when it started in the positive direction, and it reaches that here and goes even faster. So notice in the same amount of time on the way back, it will recover the distance it left, and then it's going to travel even farther in that last interval of time. And then the thing reverses direction again. Now has it hits this number. I misspoke there. It gets to be like a very, very large negative number down here, and then that number decreases, so that eventually by the time it gets back here, the velocity is 0. And so we've got like a maximum Vmax, a maximum speed there, and then it slows down. So there's a lot of stuff going on with the motion. It's slowing down and coming to a stop. and then speeding up in the other direction, and then it slows down again and eventually comes to a stop. All right, so that's what's happening with the velocity. Wow, just reading off the velocity. Now, if we look at the gradient, the slope, what we can see here, the slope is negative slope the entire time, and it's constant. So we have constant negative acceleration, and then we have a positive constant acceleration after it reaches its maximum speed here. So the acceleration is a constant until it comes to a stop. And the area, now this is where it's unique. We haven't seen this quite before. As it's slowing down in the positive direction, the area increases all the way out to here, and that area is the displacement. But then notice we'll switch the color here. We have negative area. And that negative area is getting larger, but if I add the positive and the negative area, there comes a point at which they are equal to each other. And that is this location. The positive area moving to the right is reduced on the way back with the negative area until it reaches here, and the displacement, the change in position, is 0. So what we know at that particular location is that this is the same place. We can see it graphically, and we can see it in our motion diagram. Now what happens after that is we get increasing negative area. So it's going further and further and further past where it was until it reaches that maximum. And even though the acceleration is now positive, it's slowing down, it's still all the while moving in the negative direction. And so that the maximum displacement actually occurs at the very end at about a time of 25 seconds. And so that's what we have going on with the area. So now it moves according to the shown above. A student is asked to determine the cart's displacement in the first 2 seconds of the cart's motion. His response, which is partially incorrect, is given below. So let's check this out before we get confused by the student. Want to figure out the displacement. We did this as well. So what we determined was that there is positive displacement to this 0.75, and by 1.5 seconds, it's back here in the same location, and then it continues to move even further to here. So what that means is if this was the initial starting point, it is now here, and that new position it's in, that displacement experience is due to this area that I just shaded in red over the green. And so that's what happens up to the 2 seconds point. So the displacement we're looking for is actually the area of that trapezoid. Okay, so now let's see what the student says. Student says the cart's displacement is the area under the velocity time graph to 20 seconds is shown in gray. So notice then, of course, that the student has misidentified the area. They assumed, origin error, they assumed that this was 0, 0, instead of observing that the true origin is up here. And so that's the first part of the mistake the student made. This, up until this point, that part of the area is correct, although everything below it is wrong. Okay, the area of the triangle, blah, blah, blah. Explain the errors in the student's solution. And so the student's errors has to do with the incorrect identification of the y-axis, of the x-axis, of the origin and the x and y axes. And so in this case, this bottom line where he's taking the area to is actually at minus 2.5, which is an arbitrary number. The area is incorrectly taken from v equals minus 2.5 upwards instead of between the curve and y, or v equals 0. Does the student underestimate or overestimate the cart's displacement in the first 2 seconds of its motion? Well, what we can see here is we said this is the displacement in the 2 first seconds that's It's actually in here. And the student said the displacement is all of this area. So the student overestimated. Explain your answer. Well, we would include things like the actual displacement is the area of the trapezoid from 1.5 to 2.0 seconds between the curve and v equals 0. This is much less than the area of the gray triangle computed by the student. Therefore, the student overestimated the displacement. So notice the key parts here of my answer. All right, so we're starting out with a physics principle. The area, the actual displacement is the area of this trapezoid. This is much less than the area of the triangle computed by the student. And then we have our conclusion. So we started with the physical principle and what it means for the correct answer, the physical principle as it relates to the student's answer, and therefore the conclusion. So again, in this question, if you will notice, like others we've seen, 80% or more of the time is prep to get adequate detail for our answer. I would say if we spent 10 minutes on the total question, we would have spent only about 2 writing the answer. And because we had done all that work, it allows us to be succinct.